All right. So, welcome everyone. This is the sixth session, the interactive session for the course of machine learning. My name is Sagnik. I'm a PhD student at IIC Bangalore, and I'm helping out as a TA for this course. So, this is the sixth session where I'll discuss all of week six content. So, I'll discuss problems from each of the mentioned topics. So I'll solve some problems. So I know that the week six assignment deadline has passed, but so these problems, then the technique still might help you during the exam if you are unable to solve some certain kinds of problems. So we'll do that. Right. So before I get started on solving the problem, I just want to ask you a few questions. So the first question which I want to ask is, uh, so so what is the weight update rule when we are using gradient descent? So for a perceptron, what is the weight update rule which we are using? Um, I'm unable to hear if you're saying anything. So is my voice audible for all of you? And can you hear what the other people are saying? So, because I can't hear this one guy who has his mic. You have your mic unmuted, but I am not able to hear what you're saying. So anyway, like, I'll give the answer for now. So the weight update rule that we use is so we have our weight say W, right, and we'll update it as W equals W plus um, so the weight is updated as W equals W plus. We have some learning rate, and then we have a partial differential with respect to W, right? So this is the general update rule. Say we have so the basic structure is like we have a perceptron like this, right? There will be some inputs. So there are three inputs: this x1, x2, x3, and we have the weights w1, w2, w3, and and finally we get some sort of output which is y, right? So the operation which goes on inside here is basically we have w1 x1 plus w2 x2 plus w3 x3, and then we put this. So if I call this thing as say z, so then we put z through an activation function f of z, and finally we get y basically, right? So this is the path taken in the forward direction for a perceptron. Now if I have to calculate this gradient basically, so this del j del w, right? So I can, so say I want to update w1 here, so w1 will be equal to w1 plus alpha del j del w1, right? So I have to find del j del w1. So j is the, so by j I mean the error function or cost function which you're using. So I'm calling that j, right? So we also have to decide on a certain structure for j, right? So say that usually for a perceptron or these kinds of problems we use a simple like squared error. So basically if j is half of t minus y, so t is my target value, so which is a constant, t minus y whole square, then I can find del j del w1 by applying chain rule multiple times, right? So del j del w1, this is what I need to find, right? So that this will be equal to del j del y into y del z into del z. Does anyone have a doubt with this chain, with this chain rule which I've created here? So this should work, right? So this should give me the value of del j del w1. So I hope no one has a doubt in this. Okay. Yeah, even if you have doubts, yeah, you can type the if you want to type them out. I'll keep the chat also open, so you can see. Okay, so now that we have this chain rule over here, so we can start to put these values, right? So fine, del j del w1. So del j by del y, what is this value? So okay, let's see. Where is this? So we want del j del y. So this is equal to, so if you see, j is equal to half of t minus I whole square, right? So this will become so this is basically so that if you differentiate it with respect to y, then it comes out to be t minus I basically. Yeah. Then del y by del z. It's a z is, so basically y is equal to f of z. F is my activation function which we are using. So in this case, let's say that we are using a linear activation as I mentioned here. So if you are using linear activation, it can be some. So y can be some like, so say something like kx. Okay, so k is a constant. So then del y by del z, so kz, sorry, so k times z. So del z is equal to k, right? And finally we have del z by del omega 1, so sorry, not omega, w1. So z is equal to w1 x1, so I've written it here. So z is equal to w1 x1 plus w2 x2 plus w3 x3. So del z by del w1 is x1, right? So finally we have del j del w1 equal to, so it will be t minus y into k into x1, right? And finally you can write w1 is equal to w1 plus alpha times t minus y into k into x1. So this is the kind of formula you can think of which you can use in any problem. So you to by use in any problem, I mean any problem which has this as a cost function. So you have to keep in mind, if this function changes, then we won't be using t minus y anymore, right? So this derivative does not hold. And if you don't have a linear activation, so if you have some other activation like sigmoid or something, then so this derivative won't hold, so this k won't be there, right? So only if you have these two conditions, then only you can think of using this formula, right? So don't just use it blindly in any problem. Look at the conditions which are mentioned in the problem, and then you should like figure out this. The main thing is figuring out this derivative, right? So the main thing is figuring out this derivative, and this you can easily do using chain rule. So this is the, so this always holds, right? So this will always hold. This is always valid. But so this formula is valid only when these two conditions, only when the other conditions are satisfied. So this condition and this condition must be satisfied for this update rule to hold, right? So that is the bottom line. Now okay, let's move into a problem then. So what I've done here is, so we have some like inputs. We have three inputs. So input 1 2 3, we have the corresponding targets, and we have this sort of an activation function, right? So this is called a ReLU activation, a leaky ReLU activation. So this is So ReLU is rectified linear unit, which only has this linear part, and if the if our input value is less than 0, then the in generally in ReLU the this is flat, so the output is 0 if the input is less than 0. But in this case we have a very small output. So if you see compared to, so the if the input is positive, then the output is y equals 3x, right? But if the input is negative, so x is negative, then y is equal to 0.1x. So we have a very small input value, so this is called leaky value, right? I have my initial weights here. So the for the three inputs, threshold value is -1, so this gives my bias is equal to 1 then, right? So bias is minus of threshold. Bias weight is 1 and learning rate is also 1. Okay, so what we'll do is we'll create these input vectors basically. So for the first step, so I'll write it as s1, say. So first step 1, so I have my input vector as, so I'll write the bias input first, always. So I'll always write the bias input first, so 1, and then these three inputs 1 2 0, right? My weights are, so w is equal to so w1, say, is equal to first I have to write my bias weight and then the three other weights, right? So 1 1 1 2. Okay, and now what we do is we do w this w1 into, so I'll call this x1 for now. So we'll do w1 into x1. So multiply all the corresponding values, add them together. So so our weighted output basically, weighted output is how much do we get? So we'll have 1 plus 1 plus 2, right? So this is equal to 4. And then we also have to use the activity. So this sorry, so this weighted value is positive, right? So we have to use the activation function also. So y is equal to 3x, so my y1 you can say is 12, right? And I see here that my target is 3 here. So what I can do is, so my ultimate goal is to find the final weights after this input also, this training instance also has been passed, right? So my goal is to find the final weights. I've gone through the forward path. I've got y1 equals 12. So now what I'll do is, so we'll have now if you want to update the weight, so we'll have equal to w plus alpha times we'll have t minus y into the coefficient k into x, right? So here uh, in this case alpha is 1, so I'll ignore that. So we have t minus 1, right? So this will become equal to, so my initial weight vector plus t minus y is, so 3 minus 12, which is minus 9, right? Minus 9 into k here is the derivative of this, so into 3, right? And then into the inputs. So my inputs in this case is this, so 1 1 2 0, right? So this comes out to be like so 1 1 1 2 minus 27, so release plus minus 27 minus 27 minus 54 and 0. So these are very big values. Actually I chose these numbers randomly, I didn't think of anything. So y equal to 3x was not such a good idea, I think. But yeah, so we get this very negative values. So you can just so minus 26 minus 26 minus 52 and 0, not 0, sorry, this will be 2, right? Okay, minus 52 and this will be 2. Okay, so this will be your new weight vector again. So this is now w2, you can call it. right? And again my input x2, so this is step 2, right? Step 2, x2 will be equal to 1, 1 is my bias, 0 minus 1, minus 1, right? And w2 is equal to minus 26, minus 26, minus 52, 2. So again you go through this entire step, and you can calculate this. So I don't have the answer to this. I'll probably post this in a forum or something if you really want the answer. But you can go through this process a couple of more times and find the final weight values. So if you want to do that yourself now and tell me the answer, see if you guys can match your answers, then that is fine. I'll also work on it at the same time, right? So would you want to do that, or would you want me to move on to the next problem? Again, you guys are not audible, so just do one thing. Just type it in the chat for now. Uh, if you guys want me to solve it, like if you want to solve it yourself, and I'll also solve it and we'll match our answers, or if you want me to go on to the next problem. I didn't get it. What do you mean by it is input? Oh yeah, okay, okay. So this is input. So okay. Yeah, this is that is fine. Yeah, so okay. If you guys don't want to solve it, then I'll probably post the answer somewhere in the forum, or we'll then move on to the next problem, right? So I have some page for this. Okay, so the next problem is even more involved. I'll try to do as much of it as I can. So the problem is actually okay. Let's just solve the whole problem, right? So I have this neural network with so every branch has a weight associated with it, and I have this x1 is 1, x2 is 2. I have a target value of 0.554. So everywhere we are using identity function as activation, and learning rate is zero point 0.8. Okay, so it is not 1. So we'll have to do some more multiplications, right? So you have to calculate y. So the problem is that we need to find the so after this input has been passed with this target, so we need to find the updated weights, right? So we need to update the weights of this network. We will do that using the classic back propagation technique. Now the first step is obviously to go through this entire network and find the input y, the sorry the output value y, which this network gives. So to do that, what we'll do is, so we have x1 equal to 1, x2 equal to 2, right? So my input vector right now is 1, 2, right? And since they have not given us any information on bias and all, I will assume there is no bias. So if some network's threshold is greater than 0, it will just fire, right? So I'm assuming bias and all is 0. So my input is 1, 2. So for the first, so what will be the output of 1? So what do I call it? let me call it y1, say. Okay, so I'll denote the final output with a capital Y. So y1 is the output of this neuron, so this neuron marked on. So the numbers inside are the so this is neuron 1, this is neuron 2, so that is how we'll call them, right? So for neuron 1 we have input is 1 2, weights are, so for this one we have zero point 0.4, for this one we have zero point 0.1, right? So y1 is equal to, sorry, y1 is equal to zero point 0.4 times 1 plus zero point 0.1 times 2, right? So this is equal to, so what is this? This is zero point 0.6, right? Yeah, okay. So then what is y2 now? So we have to calculate this for every neuron. So for y2 we have zero point 0.3 plus, so it will be zero point 0.6, so y2 will be zero point 0.9. Y3 is so for y3 we'll have zero point 0.4 plus zero point 0.6, so 1.2. 0.4 plus 1.2 is 1. 0.4 plus 1.6, right? Yep. Okay, let's move on. So y4, so y4 now is a combination of so the input to y4 are these three, right? So whatever output we got from, and yeah, by the way, so I'm calculating this y is just as w1 x1 plus w2 x2, like that, because the I've been given that the activation is an identity function. So if you had something else, then we'd have to put it through that function, right? But here we don't have to do that. So for y4 I have to calculate the so it will be this weight times y1, this weight, I think, yeah. So this weight times y2, and this weight times y3, right? So what is y4 then? So y4 is zero point 0.7 times this zero point 0.6 plus zero point 0.5 times zero point 0.9 plus zero point 0.1 times 1.6, right? So this will give you okay, so how much is this then? I have to use a calculator. 0.42 plus 0.45 plus 0.16, right? So this is 1.03, right? So we have y4, let's calculate y5, y6 here only. So y5 is so what is y5? Y5 will be zero point 0.1 times 0.6, so 0.1, so this weight times y1, which is 0.6, then this weight times y2, and this weight times y3, right? So zero point 0.1 times 0.6, then 0.1 times zero point 0.9 plus 0.4 times 1.6, right? So this will give me, which is this 0.06. Okay, so what is 0.4 times 1.6, right? So it's 0.79, right? So and finally we have reached the end. So y6 is the last value. So y6 equal to capital Y, the final output, and that is zero point 0.1 times, what is it, 1.03 plus zero point 0.1 times 0.79, right? So that is, so that's 0.182. So anyway, I'll write it clearly on the next page. So right now we have a target of 0.554, and our y value is 0.182, right? So so we have gone through the forward path. right? So we have arrived at the value of y. So now we need to use back propagation to go back through this network and find all the, so all the delta values, right? So we'll have a certain delta value here, which is just t minus y, right? Then we'll have delta 4, delta 5, right? So then we delta 1, delta 2, and delta 3, right? And after all these finding all these delta values, then we can start updating the weights, right? So what is delta then? So delta is equal to t minus y, right? So this is equal to how much is this? 0.372, 0.372, right? So now that we have delta, so what is delta 4 now? So can someone tell me the what should be the formula for delta 4? So the this was so this is part of the lectures actually. So it should not be that much trouble. You don't have to tell me the value of delta 4. Just tell me uh, like how do I calculate delta 4? I need the value. The value to we'll calculate. What do you do to get delta 4 from delta or any other variable? So yeah, I don't get any answers from you. So the way to do it is delta 4 will be this W4 times, so by W4 W4 6 basically, so the weight connecting 4 and 6 and into delta, right? And similarly delta 5 will be W56 into delta, right? So we'll do that. Delta 4 is W46 times delta. So this is zero point 0.1 times 0.372, this is 0.0372, right? Delta 5 is also the same value, 0.0372, because oh okay, I will just write the formula and then easier. So this is so delta 5, change color somehow. So anyway, delta 5 is equal to W56 delta. So this is also equal to 0.0372, right? So again, then we go back even further, right? So now we reach say delta 3, right? So what is delta 3? Delta 3 is so we need it from both of delta 4 and delta 5. We'll get it from both of there. So it is this weight, so this connection times delta 4 and this connection times delta 5, right? So this connection is point, so yeah, so this connection is zero point 0.1 and zero point 0.4, right? So this is W34 times delta 4 plus W35 times delta 5, right? So that is equal to just zero point 0.1 and zero point 0.4, right? So zero point 0.1, so if you see both delta 4 and delta 5 are same, so just 2.1 plus zero point 0.4 times this 0.0372 and whatever, what is that value? So 0.5 is 0.0186, right? So delta 2 again is W24 delta 4 plus W25 delta 5, right? So what will that value be? I'll just calculate the value instead of wasting time. So zero point 0.5 and zero point 0.1, right? And both delta 4 and delta 5 are same, so I'll just add these two weights and multiply it with that. So zero point 0.5 and zero point 0.1, zero point 0.6 times this is 0.02232, and finally delta 1 is w14 delta 4 plus w15 delta 5, right? So this will be again, what will it be, zero point 0.7 and zero point 0.1. So this is 0.02976. Okay, so now that we have all these delta values, the next step is just the weight updation. So then w1 say gets updated to previous value plus alpha times we have our delta, right? So we have our delta 1 times x1. Usually you would also have a derivative, so derivative of the activation function here, but since our activation is identity function, we don't have that. So anyway, you can put, so alpha was zero point 0.8, delta 1 we have got, x1 also we know x1 is 1, okay, and x2 is 2. So you can place these values and find each of the weights, right? So w1 and w2 are by w1 I mean w1 4 basically, or what is it? Yeah, so by w1 I mean so 1 between x1 and 1, right? So I'll just make that clear instead of, so w x1 1 I should say is equal to whatever I had written, w x1 1 plus, so the previous value plus alpha times delta 1 times x1, right? Similarly w x2 1 is equal to w x2 1 plus alpha delta 1, and the here it will be x2 instead of x1, right? So w x1 1 is this weight, so this one, w x2 1 is this weight, w x w x1 2 is this one, and then this one, and then this one, and this one. So when we get to the next layer, so instead of using x1 x2 you will use the values of so we'll have to use the values of these neurons, right? So you'll calculate the value of the neuron and then find and then put it in here. Oh, actually, like you don't calculate the new value. You use the previous input value. So in this case, you'll use zero point 0.6 instead of x1 x2. Right? So I'll just write that down quickly. So say w14. So the connection between neuron 1 and 4 is, so the old value plus alpha times delta. So in this case we'll use delta 4, delta 4 into we have our y1 basically. Yeah, so y1 is this zero point 0.6 over here. Okay. So that is this problem. Does anyone have a doubt in this problem? You need to solve it the entire way. So you will get how many, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 14 weight updations that you guys have to do. So and all of them follow a similar formula, right? So do you have any doubts in this? Okay. So anyone else has any more doubts in this, then please ask. We'll go to the next problem. Right. So if your mic is working, then you can use your mic. Otherwise, you can type it in the chat as well. Right. Okay. No one seems to have any doubts in this, which is surprising. But okay, fine. We'll move to the next problem. So next problem is on Hebbian learning. So will just jump into the problem, which is it says that consider a neuron with four inputs with inputs from four neighboring neurons. Okay, the learning rate is one, and threshold is also one. So the weights are this. So the weights are one. It is initialized like this, and x1 x. So we have three like three instances basically. So you need to find the final weight vector. So okay, so in this case, yeah. So let's jump in. So it has not been mentioned here. So if basically in Hebrew learning we have this threshold. So if you cross this threshold, then your the value of your output y is equal to 1. Otherwise, your output y is equal to 0, right? So we only have these two states here, and the learning rate is 1, it's given, and the weight updation is given by, again, w is equal to w plus alpha times uh, y times, so say I am trying to update, uh, so if I want to update w1 basically, so in going from w1 to w2, so we'll update it as w plus alpha times y times alpha times y times x basically. So we'll use this now. Okay, in this case, so x1 is equal to 1001, right? So and w1 is equal to 1, right? And now I'll so we will calculate the weighted input, so that will be equal to each of these multiplied, and then so the dot product between w1 and x1, so that is equal to 2, right? So which is greater than 1, implies my y1 is equal to 1. Okay, so then my weights get updated to, so w will get updated to 1 1 1 1. So basically this will become w2 then for the next step. So plus alpha is equal to 1, y is equal to 1, and x is equal to x1, right? So 1 0 0 1. So this becomes 2 1 1 2, right? Now with this w2 I have my x2, which is how much is it, 0 1 1 0, right? And then w2 is this 2 1 1 2. So the weighted input becomes still again with 2, right? So which is greater than 1. So again y1 is equal, y2 is equal to 1, right? Then w3 becomes this 2 1 1 2 plus learning rate is 1, y2 is 1, and input was 0 1 1 0. So this is equal to all 2's, right? Then for I have x3, so last one, this is 1 1 0 0. If you do this with the weighted sum, then it will come out to be 4, which is greater than 1, implies that y3 is also greater equal to 1, right? So from here you can calculate w4, or the final weight, is equal to this 2222 plus learning rate is 1, y3 is 1, so no point writing those, and my input is 1100, right? So the final answer is 3322, right? So this is my final weight vector for this Hebbian learning. So you see that in every step, so since so my inputs were like 1001, right? So these two, so the one first and fourth neuron are firing together, so their weights get updated together, right? So this is the essence of Hebbian learning, right? Then again in the next step, my the second and third neuron were firing together, right? So so those weights got updated, right? So in the second step, if you see, I went from 2 1 1 2. So the first and fourth, the weights for the first and fourth neuron did not change, they remained 2, right? But for the second and third neuron, since they fired in this step, so their weights changed to 2, right? And again for the next step, only the first and second neurons weights got updated, right? So this is how Hebbian learning progresses through every step. Right. Does anyone have a doubt in this? First of all, sorry. Okay. Since there are no doubts, we will move to the next problem. Then. The next problem is on half-feed networks. So again, this is very similar to Hebbian learning. So this involves the Hebbian learning process is still there in this case. So in half-feed network. So but in this problem, what are we required to do? So we have our three input vectors, right? Our stable unit states are, so these three are our three input vectors. The stable unit states are -1 and 1. The test case is 0 1 0, right? So we have to build the weight matrix and find the state vector for the given test case, right? So the by this stable unit states means that, so I am again assuming zero threshold. So if the threshold is greater than 0, so if the weighted input value comes out to be greater than 0, then the state goes to 1. If it is less than 0, then the state goes to 0, to -1, sorry. So for this case, so I have v1, v2 and v3, right? So I'll build my input matrix basically. So this is built like this. So v1, v2, v3, so every input is a row here. So this comes out to be, in our case, this will come out to be, so v1 is 1 -1 1, v2 is all -1, v3 is 1 1 -1, right? So now the weight matrix for a half-field network is given by 1 by n into x transpose x, right? So we have to do this. So this is 1 by 3, n is 3. I have 3 inputs, so n is 3. 1 by 3 times x transpose, right? So x transpose is 1 minus 1 1, and so this times this matrix again. So uh, this one. Okay, so we need to do this multiplication. So I'll quickly do it. I mean, this is just matrix multiplication. I think there should be. Okay, so this is 3 1 7 1 minus 1 3. So this comes out to be like so if I do 1 by 3 of every value, so then this will be 1 by 3 1 by 3 1 minus 1 by 3, right? And so 1 by 3 minus 1 by 3 and 3. Okay, so this is my weight matrix, and finally I have my test case also. So so the test case is 0 1 0, right? So if you do this, so basically this comes out to be this column, right? So this column will be selected. So my yeah, so my value will be so after this multiplication I'll get a matrix. I'll get a vector, sorry, 1 by 3 1 minus 1 by 3, right? And then you have to check so you have to compare it with the threshold, right? So I see that so the first value is 1 by 3, which is greater than 0. So my state vector will be 1 for the first case, for the first input. For the second feature I have, then the value is 1, so which is greater than 0, so state is again 1. And for the third one, the value is minus 1 by 3, which is less than 0, so the state will go to minus 1, right? So this is my final answer. So this is my final answer for the state vector for this given test case for the Hopfield network, right? So does anyone have any doubt in this problem and the solution? Yeah, someone has written cells at phi together, y together. That was for Hebbian learning, right? So that is for this network, for the Hebbian learning case. For Hopfield network, do you have any doubts? Okay, so I have one last question, which you won't probably encounter this that much, but still it's a mathematical thing. So I'll just quickly go through it. So we have to find the convolution of these two functions. So if you have to find the convolution of functions, the 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 process basically is, so you can think of it like, so we have our formula obviously, minus infinity to infinity, so f star g of x is equal to f of a times g of x minus a dA, right? So this is the formula if you want to think of it as purely mathematically. But the easier, so if you have functions like this which are given here, so a kind of a rectangle and a triangle like this, you can think of it like when these two functions are overlapping, what is the like so what is the area of the overlapping part? So that would be the value of my uh, convolution at a particular x. So the way to do it is, so I want to find f star g, right? So f star g, for that what I'll do is I'll keep f like this, so f will remain like whatever graph you see here for f of x, that will remain the same. For g of x, I'll make the graph of g of minus x basically. So that is something like so I can do it. Yeah. So this is minus 1, this value is 1, right? So this is 1, this is g of minus x, right? And now what you want to do is you want to start sliding this thing, this triangle. So we have our so if I make it on this graph only, so I have my g of minus x triangle like this, right? So this end is at -1, so I'll start moving it. So I'll start moving it So initially there is no overlap, right? But then as you move it more and more, you get this shaded region as overlapping, right? So if I move it by x, then then there's a particular amount of overlap. And when I have moved it by 1 unit, so 1 unit fully, then the triangle is fully inside the rectangle. And for a long time it just keeps it just stays inside this rectangle, right? So then at that part the overlapping area is constant, so that value will come as constant. So this is what we should expect out of the final f star g of x graph, right? So okay, let's start. So initially so uh, for x equals so say I start so this is my initial configuration. I'll remove some of the stuff which I've drawn. So this is my initial configuration, this one. So I have this like this, and this is at -1. So for x between 0 and 1, basically, so by x I mean how much it has moved. So if I move it by a certain distance x, so right, so this is my shaded area, this is the overlap, this amount is x, right? So what is the area of this triangle now? So this line over here is the equation. We have to find the equation for this line. We'll find this cutoff basically, and then we can easily find the uh, yeah. So for this line over here, so this, if I keep extend this line, so this is the line y equal to minus x, right? So this is the line y equal to minus x. Then the so the this is shifting, so this is being shifted parallel, so these two lines are parallel. So this is y equal to minus x plus something, but so the cutoff here will be x also, right? So this is basically, if I move it by distance of x, then this height is also x, this base is also x, right? So the area of that triangle will be, so then area is equal to half into x square by 2 basically. Yeah. So now this will happen until x reaches 1. So when x reaches 1, then we have this situation where this I'll erase the some of it. So when x reaches 1, then we have this situation, right? So we have this situation. I don't know why the color switched to black, but okay. So we have this situation here where the triangle is fully inside the square, right? So this happens from x equal to 1 to when x is equal to 4, right? So until x reaches 4, we will have this situation where the triangle is fully inside the rectangle. So the area, so the overlapping area is just the area of this triangle, right? So for 1 less than, I just put equal to signs here, less than 4, we have area is equal to this is a half, right? So half into 1 into 1, so the area is half, so this is a constant value now. And finally for x greater than 4, so for x actually not for, just for x greater than 4, so we'll have, so not just for x greater than 4, we have this region where this triangle will be leaving the rectangle, right? So this will happen from x equal to 4 to x equals 5. So x is the coordinate of this corner, right? So this will happen from x equals 4 to x equals 5, right? So at 5 the triangle will be here, right? So it's a very bad drawing, but okay. So the triangle will be here at 5, and after that there is no more overlap, so the value will go to 0. And for x less than 0 also, the area is equal to, the overlapping area is equal to 0. So for 4 less than x less than 5, what is the area? So we'll have this shaded portion, right? So if you think about it, this shaded portion is just minus of the, like, take the area of the triangle minus the area of this part which we had calculated earlier. So it's going out at the same rate. So the this value actually will be half minus x square by 2, right? So yeah, I think that is the right answer. But anyway, we'll just calculate once to check because I'm not very sure. So so the what is the, so if I have a random line like this, what is the equation of this line? So if I have it here, then then this is again y equals, so this y equals minus x. And what is the, what would be the y-intercept of this line? So this is slope of minus 1. So this will also go touch at 4, right? Minus x plus 4. Yeah. So this is minus x plus 4. This will be minus x plus x intercept basically. So yeah, I mean this height will be, so this height will be again x, right? Yeah. Yeah. Then we'll have again the area of this part is then so actually it's not x square by 2. This is where I made the mistake. So this will be, so the area of this part actually, this part which I'm highlighting in black is half of half. So half of the base is here is 4 minus x actually, and the height is also, so this height is equal to this length here, right? So the that is also equal to 4 minus x, so that is equal to 4 minus x whole square. So x is the x coordinate, right? So you have to keep that in mind. So this area will be so the area here will be half minus this value, half times 4 minus x square. Okay, so this okay, this looks good. And this will go until 5, and for x greater than 5 the area is again equal to 0. So if you plot this, so the graph will be something like this, where the graph of f star g of x basically, the convolution. So initially it up till x equal to 0, so this is x and this is f star g, right? So up till x equal to 0 it is all 0. Then from x equals 0 to 1 it's a x square by 2, so it's a parabola, right? So this is a parabola. Then from x equals 1 to 4 it is the value is fixed at half. So if you calculate the value at x equal to 1, then this value comes out to be half, by the way. So for x square by 2, it's not like there's any jump discontinuities or anything. So from x equal, so it's at x equal to 1, this is here at x equal to 4, and from 4 to 5 again. So this is the this is this parabola, half minus half of 4 minus x square. So if you plot that, you will get this, and this is 5, right? And after 5 it is again 0. Okay, so yeah, if you see all the values everywhere, then everything seems to check out. So this is the graph for the convolution for the functions just shown. I'll remove these marks here. So these are the two functions, and this is the convolution, the graph here in black, right? So this is the convolution. Okay, so that was actually my last question. So if you have any questions on this, just a second. If you have any questions on convolutions, then yeah, please let me know. I don't know why the screen is not updating here. So if you have any questions on convolutions or any other doubts now, then you can ask me any doubts that you want. Right. So much. So I'm done with the problems that I wanted to discuss today. If you have any questions on any topic, then you can please ask. So from week 6, basically, I'm covering week 6 today. Week 7 and week 8, I'll cover in the later sessions. Those don't have a lot of content. We'll figure out something that we might do in those sessions. Okay, you want to know about filter, is it? So filters are basically used in convolution. So this what I showed you, this example was a mathematical variation of convolution. What I'll do is, so I'll create, keep this. So I'll create a new slide actually. Yeah. So this is not needed. Okay. So I'll quickly describe. So what we do for our machine learning algorithms is, so how to use a filter? Yeah. So what we do in our machine learning algorithm is in a CNN basically is we'll have some sort of an image, right? So we'll have this. So this is my image. So say this is some value, say 100 by 100. Okay, so 100 pixels by 100 pixels, I have this one image, and when I am passing it through my CNN, I will have some filters, right? So say this is, I'll draw it in a different color. So say I draw it in green. Okay. So say this is my filter, right? So this is filter. Usually you choose your own size for filter. So say this is 5 by 5 filter. What we do is we put this filter here, right? So 5 by 5 filter means there's 25 sorry, there's 25 values here. So the filter, all of these squares are matrices, by the way. So when you are actually building your algorithm, so this filter and image, all of these are matrices. So the image is a matrix of pixel values, the filter is a matrix of weights, you can say. Okay, so we'll have basically numbers in this filter. So 1 2 3 4. So we'll have numbers like this, and so say like this all the way in this filter. You can have any number that you want, but anyway, so we'll put this filter over here at the top left corner. So we'll start over here, and so for every, so this filter now overlaps with 25 cells of the image, right? So 25 entries in the image and the 25 entries in the filter, we'll multiply those two values. So we'll have a total of 25 multiplications. And if you are also looking for any threshold, any bias value, then you add the bias, and then you'll get one value out of, so out of this you'll only get one value. So in your new uh, so after the convolution operation, you'll have a smaller matrix. So this entire thing will just boil down to one value over here. So one matrix entry over here, right? So that is and then again you'll shift this by one cell, right? So you'll shift this filter by one cell, do the same thing, 25 multiplications plus bias, and then plus bias, and then again you put it in the next cell, right? So this is how you build this new matrix, and that is how you use a filter, right? Yeah, that is a basic idea. So keep shifting this by one cell. So you can choose this by how many cells you want to shift by. So that is called the stride. So if you want to shift it by two cells, then you will have to mention it, and your stride will be two in that case. This keeps shifting. Right? Does that clear your doubt? Okay. Any other questions? Yeah. So what I showed you, this is if you have some simple functions like this, so like this rectangle and a triangle, then you can use the area method instead of doing this integration. Okay. But if the functions that are given are very complex, then instead of doing all this area thing, just find the just do this integration. So that is easier, right? So this is it's not difficult. So you'll be given f of x and g of x. So f of x will be, so say f of x is x square, g of x is some weird function, so x cube or something. Okay, then you put them here, right? So then this integration will be minus infinity to infinity x square, a square actually, a square times x minus a cube dA, right? So this is a an integration which you should hopefully be able to do, right? So from minus n, so again I have no idea if this is bounded or unbounded. This is probably unbounded, but okay. So this is how you do it for not so good looking functions. So here also, if you want to, then you can use that. But in this case, the functions made some very simple figures on the Cartesian plane, so it was easy to do this area method. Are there any other questions? RNN. So I did not discuss anything on RNN because honestly, there is no way that I can solve an RNN problem by hand. Well, no one can solve an RNN problem by hand. It is just too difficult. So if you have any specific doubt in RNN, then you can ask that. In general, I mean, I don't have anything specific to discuss from the RNN section myself, which I found very which I found very worth mentioning. I did not find anything like that as a professor had mentioned, which you need to keep in mind or you need to solve problems. So types of RNN. I mean, you can go through the lectures and you will find your answer, right? If you want the types of RNN, there's no point asking me. But okay, so instead of sharing the screen, I'll share my laptop screen, and we'll look at the RNN types there. If you have any doubts from there, you can ask me, right? So I'll stop sharing the screen by the way, and I'll share my laptop screen. Right. So here it is. Um, just give me a second. I'll open the chat here to see. Okay. So yeah, we have RNNs. We have there are the types of RNN. So okay, this is all. So one type of RNN is obviously the yeah. So it is there in these two slides basically. So you can think, so one kind of classification of RNNs that you can do is like based on the kind of problems that it can solve. So you have one-to-one networks, one-to-many networks, many-to-one. So one-to-one networks can solve. So this is basically simple ANN you can think of. Okay, one-to-many. So in case you have one so say something like an image, and you want to describe this image. right? So that will be many words to describe one image, right? So that is a one to many sort of classification. Many to one, again, if you so yeah, examples are given here anyway. So a sequence of words. So say you have been given a sentence and you want to find the sentiment of that sentence. So is it happy or sad or angry? So usually this is used in customer review studies, right? So many to many. This is so if you have a sentence and you want to translate that sentence, right? So this is used for translation work and all. But also for something like speech recognition, like text to speech or speech to text, right? So it is converting your speech into text, or it is converting your text into speech, right? So this is used for that also. And finally, many to many is like here you can see an example. It is video frame classifications, right? So video frames are just one image, and then you'll have some sort of classes maybe, or describing the video. So that's a many to many application. So this is one kind of application. So this is one kind of classification that you can do for RNNs. uh, the other is like you can say, so we have a plain simple RNN, which is a single layered RNN. And then from there you can go so if you want to go backward or forward in time, then you get a bidirectional RNN. Or if you want to stack multiple RNNs together, then you will get a multi-layer RNN. So those are some of the other forms. Okay, so some other types of RNNs. And so the problem with normal RNNs is they have a very major problem of vanishing or exploding gradients, right? So during back propagation, the derivative of cost with respect to weights is either very small or very large, okay, which leads to very drastic changes in the weights, which is not good at all for our network. So if you have vanishing gradient or exploding gradient, then that creates a problem in basically learning. So learning the weights becomes very, very difficult if you have this problem. So to handle this, here it's written short long-term memory. Actually, it's a long short-term memory, okay, LSTM. So you have an LSTM which uses, so an LSTM basically it so here's a comparison. So an RNN just has a normal activation, and that's it. But an LSTM has a large number of gates, and it can choose whether to store a particular input in its memory, or not store it. In which So if it wants to store it, then it will open the memory gate. Otherwise, it will not open. So then that input gets deleted if in case the memory gate doesn't open. And the condition for that is encoded into the LSTM cell. So that is the so this is almost the final classification of an RNN. And so the nowadays the a more advanced version of LSTM is called transform. So which is used in all language models, right? So Google uses it in their Google Translate. Uh, they use transformers. Obviously, GPT-3 and Chat GPT, those are transformer-based models, right? The T in GPT stands for transformer. I forgot what the other two were. So that is the kind of classification in different forms of RNN. So actually, there is no way that you can ever solve an RNN problem by hand, because the machinery is just too difficult to go through by hand. RNN problems are always so RNN problems means like machine learning problems which require RNN are always solved in a computer. They are not solved using by hand. So which is why even the professor or even I could not cover any examples by hand. So any hand calculation things, because it is just not possible. Okay, so that's it. Any other questions? And in the presentation here also I have it. If you have any questions from this, also you can ask. Wait. Yeah, any more classes? Yeah, we'll have. So I am required to do a session for week 7 and week 8 also. But since they don't have a lot of mathematical problems and such, I'll see what I can do in those sessions. Maybe we can look into a bit of coding. So we can look into a bit of coding, some different kinds of, say, a decision tree, or we can train random forest, or we can try training an ANN to do something. So the most popular example is training an ANN to identify handwritten digits. So if you would want me to do that, then I'll do it. Otherwise, I'm not sure. I have to discuss with the NPT here T on how to take sessions for week 7 and week 8 then. Okay, so I'm not getting any response. I will check with the NPTEL team on how we can do the sessions for week 7 and week 8. But yeah, if they're not able to give me a solution, then I might just go for a coding session where we can look at, we can try to train an ANN, right, using all of these concepts. So for forward propagation and back propagation, so we'll have codes written for those and we'll try to do it. So it is obviously, so during actually, so during coding of a machine learning algorithm, it is not required that you always write your own forward propagation and back propagation codes. So there are a lot of libraries and frameworks which allow you to, if you just tell it the structure of the ANN, it can automatically do the forward propagation and back propagation and calculate all the gradients and everything for you. So coding it is very easy, but yeah, we'll try to do it from first principles. So okay, are there any more doubts? If there are no doubts, then we'll close the session. Okay, thank you. No problem. So okay, I don't see any other doubts. I'll wait for some time in case you guys are typing something. If not, then yeah, you can feel free to leave the meet. Okay, there doesn't seem to be any more doubts, so we'll just call it a day then. Yeah, thanks everyone for joining. So I'll see you again next Monday. And before that, if you have any doubts, then my other TAs also have their sessions. So yeah, you can ask them as well. See you. Bye bye.